Hello YouTubers and fellow hams. Well, it's project day today. I got a box in the mail. It's a standalone Whisper beacon built with an Arduino and an SI5351 clock generator chip, a GPS receiver, and a few other goodies. And we'll get to that in a second. But first off, I thought, well, since we're talking about Whisper, I might as well give you a quick, brief little history of Whisper. So Whisper stands for Weak Signal Propagation Reporter. Now, it's a technology and a protocol that was developed by Joe Taylor, K1JT. He's the guy behind the WSJTX software that many of you are probably familiar with, that does the extremely robust low-power modes like JT9, JT65, and of course FT8, which is all the craze right now. These modes were originally designed for moon bounce and other very weak signal operations. And as part of that, Whisper was developed. Now, Whisper is a beaconing protocol. It's extraordinarily robust, requiring as little as negative 28 dB of signal to be decoded, which is a very, very, very small amount of signal. Literally a whisper. It only sends 3 bits of information, or 3 pieces of information, I should say. It sends the call sign of the transmitting station, the Maidenhead grid locator, which is a map. For those of you that are not familiar with that, the entire Earth is divided into grid squares and subsquares to ease locating places on the surface of the planet. It's called the Maidenhead grid locators. What else does it send? Oh, and it sends the power that you're transmitting at. Now, the idea is that if you have enough stations out there sending out these beacons and receiving, that you can develop a sort of map or indication of propagation conditions around the planet in real time. It's all volunteer. Anybody running the WSJTX software can participate and transmit Whisper broadcasts. A lot of stations will be at very low power, a watt, a half a watt, or even less. And it's surprising how far your signal can get. Sometimes it's fun just to set it up and broadcast at half a watt, leave it on 20 meters for a few hours, and then go to the map and see how far your signal's gotten. There's a couple of different mapping resources out there. Here's a picture of the official Whisper map. And this shows you the stations that are presently active on 30 meters. Now, there are stations active on all the bands pretty much, all the way up through 6 and even up into VHF sometimes. It's a pretty neat thing. I've used it quite a bit when I'm playing around with antennas just to see how far out I can get. And with a half a watt, I've gotten across the pond to other countries with Whisper. So it's a pretty neat protocol. But what we have today is, I have right here a box from ZachTek. Now, ZachTek is run by this gentleman here. He builds interesting little kits or projects, including this particular one, this Whisper beacon that we're going to be looking at today, which he sent me. It's based on an Arduino and uses the SI5351 clock generator chip, which I've used in my 630 meter CW transmitter. It's a neat little chip. It lets you create up to 3 clock sources, square waves, at a broad range of frequencies. And there's an Arduino library for it that makes it very easy to program, which if you go back and look at my 630 meter transmitter project video, I have lots of details and information there on how I used that chip. So what Harry did was he used an Arduino and that chip to generate the signal, and he has a GPS receiver on board. GPS is important in this case because of 2 things. One, Whisper transmissions have to be synchronized. They have to start precisely on the top of the minute, and they have to be receiving then on precisely the top of the minute so that they all start transmitting or receiving at the same time. And also the locator is important. Now both of these type bits of information, the location and the time, can be achieved with a GPS receiver, and that's what it uses that for. So it's a nice little standalone beacon. Very low power. It draws 250 milliamps when it's in transmit mode. It has the ability to band hop and do broadcasts on up to 4 bands. And in my case, I asked Harry to send me the kit with low-pass filters for 4 of the bands, 80, 40, 20, and 10. So I'll be setting it up and letting it run for a while, beaconing on those bands once I get it going. But first, we got to open the box and take a look at what's inside. So let's do an unboxing. So here's the box I received. Let's have a look and see what we got inside. I need more space here. Okay, looks like Harry sent me a little letter here, some information. Okay. Oh, we got a schematic printed out. Very nice. Looks pretty complete, and packing material. Fire starter, kindling. Okay, we have stuff. Oh, I get to do some assembly. I get to wind a crap load of toroids. Oh, joy. I know what I'm doing all day today. This is the low-pass filter kit. The board, as it is, produces a square wave, and that's, of course, very noisy. Off of Harry's website, I found some photos he put up of some oscilloscope tests, and we can take a look at those. He shows the unfiltered output from the square wave, and there's a little ringing on it, I think. And then he shows the harmonics that it produces. Tons of harmonics. That's what these are on the spectrum scope. And then he shows the cleaned up wave after it's passed through the low-pass filters, and you can see it turns into a nice sine wave. And then the harmonic display again after passing through a low-pass filter, where all those spurious harmonics are then eliminated, and you can see there's a primary signal that's very strong, and the harmonic is greatly reduced. So this is the low-pass filter kit, and it looks like he's got several toroids in here, plenty of wire and other components, and a PC board that will be a daughter board on top of the main board. So I'm going to have to assemble that. We've got a pack with a USB cable, more toroids, wires, PC board blanks, and a solder sponge, an SMA to N adapter. That's a weird choice. But I guess, you might have all kinds of cables. An SMA to, hopefully that's SO239. Yes, it is, SO239. Some strapping material, various components and things. Power lead. Looks like it's a little over compensated for the small amount of power draw. We'll get into all that. And then this would probably be the main board. Yes. Another USB cable, some instructions, a GPS antenna for the GPS receiver, nice long cord on it so you could position it a ways away from the beacon if you needed to, and this would be the beacon itself. It's all very nicely packaged in static-proof bags. There we are. An Arduino Nano. This is the GPS receiver. That's probably the SI5351. That's the line driver. That's the power amplifier. Some various support electronics here. USB, micro USB port there, which will bring in power. So it's going to have 5-volt power requirements. I'm probably going to build it into an enclosure and use a 7805 so I can feed it 12 volts. I actually mentioned to Harry in a comment as we were talking about this that it might be nice to have a 5-volt regulator on board so you could bring in 12 volts directly, because I figure that many people are going to have existing 12-volt battery setups or solar setups, and they'll want to power this thing with 12 volts, which is what I'm going to do. All of my systems in here are 12 volts, so as I said, I'll probably build it into an enclosure. This is the GPS antenna input over here. This is the RF out over here. There's space on the board here for a single low-pass filter. So if you were building this for a single band, you could build on just one low-pass filter and have a complete standalone board. It's a nice little board. Oh, look, he's got a label on the back with a serial number, hardware version, power requirements, made in Sweden. That's interesting. And then the model number, WSPR-TXLP1. So the main board comes pretty much assembled. This wire is a link that bypasses the filter if you want to use your own external filter. But as I said, I'll be building the 4-band low-pass filter for this guy. Today, I don't know how much of that build video I'll film. This could turn into a very long video if I filmed the entire build, so I'll just do a few highlights, I guess. Well, I'm getting ready to wind the toroids and populate the board with capacitors, which are all surface mount. He has a nice sheet here that has diagrams of where all the coils are on the board and spaces where you can write in the values and where you can lay the inductors while you're winding them before you populate the board. On the back is a table that shows you all the values for each band. 137 kilohertz all the way up to 4 meters, 70 megahertz. And then for each band, he shows the whisper frequency, the values for C1 and C4, C2 and C3, the number or the values for L1 and L3 and L2, and then the number of turns that you're going to do. All the data is right there. So you can go through for each of the bands that you've got, make your notes on this side, and then set this aside, and while you're winding the toroids, you can lay them here. And then when you go to populate the board, you just take them off one at a time and solder them in place. And the same thing with the capacitors, you can lay them all out here. So that's the next step. I'm going to lay all the components out off to the side. Then I'm going to plug the soldering iron into the inverter and start doing some soldering. Man, I hate surface mount soldering for these little capacitors. They're tiny. But you have to do it. It's a little bit of work for this low-pass board. The final part that you do, there's a pin header on the board and a socket. You have to solder the socket onto the whisper beacon board and solder the pin header on here. And I'll show you a trick for that when I get to it. So, time to start winding some toroids. I did a tutorial video on winding toroids, or I think I talked about it in a couple. The video where I built the QCX QRP transceiver. I think I talked about winding toroids in that. And if you look for my video on a common mode choke, or on building your own 9-to-1 un-un, I talk about winding toroids there, so I'm not going to be redundant here. But anyway, I've got some work to do. Another thing I should point out, when that's nice. I'm glad he did that. Okay, the parts bag for the mezzanine, or the filter board, he has the components for each of the filters in separate little baggies, and they're conveniently marked. This one's marked 20 meters. So that's got the capacitors already in there, and he's marked the bags for the capacitors, 180 picofarad. I can see that right there on the label. So you don't have to try to figure out what capacitors are what. He's already sorted them for you and marked them all accordingly. So there's the bag for 20 meters, there's for 40, there's for 10. That's the board itself with all the standoffs. And here's the bag for 80. So I specified when I ordered the board from him what bands I wanted, and he conveniently packaged all the parts individually, so you don't have to hunt out your components and figure out which ones are which, and you're not going to get the wrong things in the wrong places. Very convenient. Thanks, Harry. That's good thinking, man. I dig that. This is the filter board here. Standoffs for mounting it to the beacon. The board itself conveniently already has the transistors and the relays, and the oh, that diode's not installed right. I'm glad I looked at that. I know you can't see that on the camera, but the D2 here, which I think is a goes across the windings of the relay to absorb a spike. When a relay is disengaged, the transistor releases its drive. The magnetic field around the relay's coil collapses, and that sends a spike of energy back, reverse polarity back to the transistor. So it's common practice to put a diode across the relay coil reverse biased, and that way when the magnetic field collapses, the current flows through the diode instead of going back and slamming the transistor. Otherwise you can have that little spike damage your driver transistor that fires the relay. Alright, here's the completed filter board. I wound all those toroids and soldered all those little surface mount capacitors on there, and I'll tell you, this is not a beginner's kit. Surface mount is not fun to deal with. It's teeny tiny. These capacitors, some of them are the size of pepper grains, and you can see the solder's a little blobby, but I got it in there. My eyes are not what they used to be. Anyway, the last thing I need to do is this pin header that connects the two boards. You've got a socket and a set of pins. I haven't soldered them yet because I wanted to show you this trick. I put them in here and they're loose, but by putting them in and putting the boards together before I solder those pins, I'm assured that they're lined up. If I just soldered the pin headers and the socket on the separate boards, one of them might be at an angle slightly, and it might make it hard to get the pins on. So what I always do is I'll put the boards together with the connector in between connected, and then solder these pins. And by doing that, I'm guaranteed that everything is lined up. And that's really all I have left to do on assembly, is solder those pins, the interconnection pins there, and I'll be ready to power the board up and see if it works, or see how it works, or see how well it works. So I've got the Whisper beacon assembled, and I've got it plugged into the computer. Now, the configuration, well, Harry wrote a really nice program for configuring the software under Windows, and here we can see a screenshot of the configuration program, and it does let you completely control the device and set it all up, set it up to beacon on different bands, the band hopping filters. You can tell it what filters you have on what bands, and it's got a signal generator functionality down here where you can set a specific frequency and tell it to just start generating a signal on that frequency. That's kind of nice. Could be useful in the shop or on the bench. The unfortunate thing is that this software is Windows only. So if you're running Windows, no problem at all. You just plug the beacon in, run this software, and you can configure and control it, tell it what to do, and set it on its way. But I'm not running Windows. I'm running Linux. And he wrote this in Delphi. And although Delphi does cross-compile to Linux or Mac, he was having some trouble with the serial library that he used, and he couldn't get it to cross-compile. He's going to look at that further. But all is not lost if you're running Linux or if you're running a Mac. It is an Arduino, and it has a serial port. So when you connect it to your computer. It creates a serial device, and you can talk to it with a terminal. I have the Arduino environment running, and I have the serial monitor up, and as you can see here, we are talking to the device. It's giving us all of its information. Over here on the left, these are response codes. He has a nice serial interface to the device, a nice API, application programming interface. He sent me the document. It's fully documented. Here we go. These are examples of the commands that you can send to it. Parameter, and then value, and then a description of what the parameter does and what the value is, and what the fields are that you send to it. Now that sounds all very complicated, but it's really not. For example, let's take a look right here at dat call sign. If I can get my highlight to work right. So the dat call sign command is what you use to set or get the call sign that the unit is using. So the command here is in braces DCS capitalized. So this is verbatim. This is what you would type to it on the serial port. Brace, DCS, brace, and then either send or get, whether we're setting the call sign or getting the call sign, and then text, 6 characters. So that's the field length and the type of field, so it's text. So let's try that as an example. We'll go back here to the Arduino serial window, and I'm going to type in, and you can see I've already done it here, and there was the response, but we'll do it again. We'll type in brace, DCS, brace, G for get, and that's going to get the call sign. And as you can see, it responded immediately, DCS KB9RLW. Let's look at another command here. How about the bands? Band transmit enable, OBD. Okay. OBD. So I'll go back here, bracket, sorry, I was saying brace, it's bracket. Is it BD or DB? I keep getting those confused. OBD. Okay, OBD, OBD, OBD. OBD, bracket, space, G for get. And then it gives me the status for each band, what bands are enabled. And these numbers correspond to the table on the page in the documentation. So band 0 is 178 kilohertz. Band 1 is 630 meters. Band 2 is 160 meters. Band 3 is 80 meters, which I have the filter installed for, and you can see here band 3 is enabled, which is 80 meters. So that's how the API works, and you can control the device. It's really not all that complicated. I've been able to completely configure and control it by using these individual commands and sending it the information that I need. Current mode, for example, up here, CCM, is setting the current mode that the unit is operating in. It's a text field. S for signal generator, W for whisper beacon, or N for none. So if I look at the current mode, CCM, we'll go back here, bracket, CCM, bracket, G for get. Current mode is none. And this brace, TON, transmit enabled, is currently false. It's not transmitting. So if I wanted to make it start transmitting whisper, I would just put in brace CCM our bracket CCM, set, S for set, W for whisper. And the light started blinking on the device, and we can see that it is ready to start transmitting on 3.57, well, the whisper frequency for 80 meters, which is actually up a little bit from there. But I don't want it to transmit. I don't have an antenna on it, so I'm going to set the mode back to none. And it came back and it told us that the current mode is now N for none, and transmit is false, disabled. So that's how the API works with serial. So you can configure it if you don't have the software, just using a terminal program and a little bit of text entry. It's really not that difficult. It's pretty straightforward. Props to Harry for setting up this API. This should also allow you to develop your own software if you want, since everything is just serial communications and these commands are pretty straightforward. It should be easy to write something up in BASIC or Python to talk to the device. In fact, I am planning on writing something in Python that could then be used by Linux and Mac users. It'd be simple, text-based. You'd run it in a terminal and it would have a menu system. It'd be straightforward, easy to work with. But that'll take me some time to do. But I do plan on doing that since I'll be using this device pretty regularly. Also, Harry has told me that he is still looking into cross-compiling with Delphi, so he may yet be able to release his control software for Linux and Mac as well. That'll be in the future, hopefully. And I'll let everybody know if I develop a text-based Python program or something. I'll let everybody know once it's available and make it downloadable for controlling this device. So that's how the software works. It looks complicated at a glance, but it's really not all that hard to work with. So here it is, beaconing away, band hopping on 80, 40, 20, and 10 meters. I let it run all night, and I was very surprised at the results this morning. Here's a map of 40 meters that I looked at, and by golly, this little 200 to 300 milliwatts of power was picked up in Antarctica on 40 meters sometime last night. I think it was probably early this morning as the gray line approached. It's been fascinating to look at the map this morning and see where it was heard on the 4 bands over the evening. And I've been looking at it this morning on 20 meters, and I watched the propagation stretch out to the east and then come across the country to the west. As my map hits changed on the map. So it's a fascinating little device. I looked at his site, and I think it sells for about $69 US, which is not bad for a kit that's built pretty well. The small issue with the diode is probably a rare one-off that just happened in my case. It's not likely that that's going to happen on others. And he was very responsive about that. That's one thing I really enjoyed about the interaction with Harry on this. He was very responsive. He answered my questions promptly. So I feel very confident purchasing any of his other products in the future. As far as this beacon, what am I going to use it for? Well, I'm going to use it every time I play with antennas. I do like to use Whisper as I experiment with antennas just to see how far the signal gets, and to see if there's any directionality to it. It's a useful tool. But it's always been a bit cumbersome because I've had to fire up the Raspberry Pi, use one of my radios, tie up one of my radios in order to do the Whisper test. Here, I'll just be able to plug this in. The setup that you configure it with, you can configure it as a startup mode. So when I power it up, right now, it's automatically going into beacon mode and band hopping on the 4 bands. However you want to set it up, you can store that configuration and have it as a power-up mode, making it a truly standalone device. I'm going to build it into a small enclosure to keep it safe, and I'm going to keep it on hand. And every time that I need to or want to play around with antennas or experiment with Whisper, I'll just pull this little guy out and plug him in and be on the air. So very convenient. Hope you enjoyed that kit build. I'm sorry it was such a long video, but there was a lot of information to cover. So until the next video, thanks for watching. If you enjoyed the video, don't forget to give it a thumbs up. Also, if you're not already a subscriber, click to subscribe. Join us on the Facebook channel for discussion about the videos. And if you'd like to help support this channel, please click to support me on my Patreon page.